the event that we put together for you tonight with myself and Molly Steenson is about AI, artificial intelligence, and it's about perhaps what AI itself is about. We want to start by asking, what is it that we mean when we talk about AI, when we refer to this thing? It's quite possible that in the near future, the idea that at some point, all of the technologies and tricks that we today call AI were once thought of as a single thing, a single technology, will seem naive and maybe even dangerous. Now, of course, in the history of AI, it has gone through many different ups and downs, the AI winters, as they've been called. But one of the persistent things about AI in its history is its relationship between the technology and thought experiments about the technology. That the philosophy of AI, or the philosophy about what AI might be, and the actual technologies that AI becomes go back and forth, one informing the other, informing the other, informing the other, and this is no less true now than it was in the past. Especially now, perhaps, as AI is put forth as in a geopolitical context in which countries and blocs claim AI as part of their strategic future. This back and forth between the fictive and real continues at a different scale. So today's presentations, however, are less about philosophy and the possible and the future, and more about how AI actually works today. AI is already an integral part of the world's most important platforms. It makes things, it puts them in motion, and it ensures that they show up on time. It sees you and predicts what you want next. In turn, you may see and feel the AI, you may not see or feel it, but the more you use those platforms, the more you are training the algorithms that run them. And thus, we make worlds. If AI builds worlds, then what is the role for architects and designers in that world building? This is one question. Another is how, and indeed if, design can steer platform scale AI in terms of how that AI steers society. So I'm going to go first, and I will present some recent work and thoughts and research on this topic, and then it'll be my pleasure to present Molly Steenson, and then we'll have a bit of Q&A and some discussion afterwards as well. So I will first say that what I will want to talk to you about tonight is very much work in progress. I'm really primarily a writer, and so the book that I'm writing now is about the artificial, not just artificial intelligence, but other kinds of forms of the artificial as well. And so what I want to talk about today is maybe part of one chapter within that larger discussion. A first idea I think it's important I want to put forward is that the work has to do with the relationship between AI and the city, AI urbanism. And this has to do with not only how we apply AI, but how we define what AI is in the first place. Thinking about AI as an urban scale phenomenon, as opposed to a brain in a box, changes how we define it, and how we define it changes what we might want to do with it. And specifically, It means that AI is all about sensing. How it senses the world and how it thinks about the world are not two different things. This is the fundamental lesson. So, very quickly, I also want to say that in the New Normal program here at Strelka, over the last 2 years, we've undertaken a specific research workshop on AI urbanism in partnership with groups at Google Research who've come out here and sat and worked with us through some of the more difficult issues that they're thinking about and we're thinking about as well. One of which is the role of AI as a geopolitical technology, both as something that is proposed as an important part of a geopolitical arrangement or is imagined as such. In essence, when we say algorithmic governance, when we imagine how algorithms govern us, what do we mean? What might we mean? What could it mean? So in these research workshops, we bring the problems and ideas that we think are most important, that we are less sure about how to answer, or even if they're the right questions, and we work it through together. And they've been enormously productive. The research that has come out of this, and I'm just going to show you some of the sample artifacts from this research as well, has also been enormously productive. It's been an important part of our program, not only in how we think about AI as a topic, but how we think through the question of AI as a way to ask questions about other things that may, at first glance, not seem to have very much to do with AI. Now, let me talk a little bit more about why I think it's very important to define AI, or how it is that we define AI changes how we think about what it might do. You're probably familiar with Alan Turing and the Turing test, which was one of those philosophical thought experiments that he proposed in 1950. In his version of this, he asks if you have a person in a computer, and you can ask either of them, both of them, as many questions as you want, and you can't tell which one is a person and which one's a computer, he asks, is this not a sufficient condition to say that the computer is in some way intelligent? The problem, though, is that this has become instead a necessary condition, that we think that unless a computer can pretend to think how we think that we think, it's not intelligent. This anthropomorphism, the idea that human intelligence is the norm, is the criteria against which all other intelligence must be measured, has set us off on the wrong track. So one of the first important ideas that we work with is to try to move past these anthropocentric models of AI. What does that lead us towards? It leads us towards something more like AI in the wild, AI outside the black box, AI at landscape scale that is sensing and thinking the world on its own in different ways, not like we do. It leads us towards understanding cities as not just made of steel and code and glass and brick, but also of living creatures and phenomena, and they're intermingled together in strange and peculiar ways. And when we layer artificial intelligence on top of all of these, very interesting things begin to happen in the evolutionary dynamic of how those things interrelate with each other. One way we think about this is what we call the synthetic garden model of AI. For this, we mean that you sort of imagine a field in which there are lots of little species, bugs and flowers and birds and mammals and maybe some people. And they all sense the world in a slightly different way. but somehow it all adds up to a coherent whole. Each has their own, what the Danish philosopher Jakob von Uschkel called Umwelt, their own little world that they live in. If you imagine not one AI at urban scale, but hundreds or thousands or indeed millions, each also has its own little world that it lives in. It senses the world in a particular way. It thinks the world in a particular way. None has an overarching view of the whole. That's more like what we have. It's more like what we want to design. Now, if we take this more evolutionary approach, it means that some of the things that we know about how evolution works also apply to how this works in a more technological complex. And I will talk more about this at the end of my talk. For example, predator-prey dynamics, how some things are looking for other things, how some things are trying to hide from other things, how things evolve in relationship to looking for other things, how things evolve in relationship to how successful they are in hiding from other things. These kinds of dynamics, the evolutionary arms race between these little AIs that sense and think the world in their own specific ways. We also see this. We also see this happening, and we also see this dynamic as part of what we may want to design. Now, one of the interesting things about this is that this evolution, in some ways it's like ours, in some ways it's not like ours at all. For example, for us, for animals, each of us has 2 eyes, 2 ears, nose, mouth. We all have our individual sensory mechanisms, one per body. For AI at landscape scale, you may have one sensor, a camera, for example, that could be connected to 1 or 2 or 3 or 4 or 5 different AIs that might access that sensor at different times. For one AI, it may connect to this sensor and another one and another one at this point and another point. They're all mixed together. So the sensors and the, quote, brains link together in different ways. This is not the tetrahedral body plan of the animal. It's a different dynamic. So, even though we think of AI, or we want to think of AI as not only in relationship to anthropomorphic models, we are still part of this drama. We are still in the city with it. We also come equipped with an extraordinary array of sensory faculties, which we augment with media and technology, including these black slabs that we carry around in our pockets that we still call phones, that produce artificial images and sounds. And so we too are situated inside this synthetic garden at the same time. Sometimes we're the protagonist within this garden. We are the main actor. We might supervise an orchestra of little sensing technologies on our behalf, each capable of sensing or processing the world in different ways, each capable of having its own intelligence. But sometimes we're not the main point. Sometimes we are not the center of the story or the subject of the scenario. We are instead the subject matter. Perhaps we are looked at and observed, or perhaps we're ignored. We're not an essential part of the drama because something else is. Now, what I want to suggest is that on the one hand, we don't want to see this entirely in relationship to a an anthropomorphic projection to see AI in terms of how we see ourselves, nor do we want to exclude ourselves from this scenario. We are part of it. And in fact, we're bound up with it. We are mixed with it. We are connected with it. It's not about human versus AI. The Turing test model of it's either a human or it's an AI has confused us. It's always humans and technologies mixed together. Human or not human is not the point. It's always a mix. Now, even if we might know this on some intellectual level, we can't stop ourselves from projecting psychologically onto AI or machines what we imagine them to be, or what we imagine they must imagine us to be. And this projection and identification, this is a therapeutic robot baby seal that is popular in Japan. It gives the elderly people who use it as a therapeutic device comfort and calm, but it doesn't actually love them. They think it does, but it doesn't. And yet it's always easier to make a machine that does the things that make you think it loves you than to make one that actually does. This is also an urban design principle. So, as we investigate these matters, one of the things we like to look for is not the norms, it's not the way things, how things work when they work the way they're supposed to, but what are the strange things that are happening that might give us a clue as to where things are going? How are the odd things and the errors actually turn out to be the path forward, or what the future might look like? So one obvious place to start with this is these deep dream images with which you might be familiar. This was a project that came out of Google Research where they, for those who are not familiar with these, I'll summarize quickly. What if you asked an algorithm that was trained to find dogs in pictures, to identify dogs in pictures, and you gave it a lot of pictures that do not have dogs in them, and asked it to find dogs in them, to identify a part of the picture that seemed most dog-like, and then you do a kind of find edges function, and then you give it that same picture again, and again, and again, and again, and again. Eventually, the AI starts to hallucinate dogs, as you see here as well. This is strange. This is interesting. This suggests that AI is capable of things that we perceive as a kind of creativity, dreaming even. That's interesting. And it leads us to then look at the phenomenon of apophenia more generally. Apophenia is the term for false pattern recognition, where we see a pattern that's not really there. And as you notice, even though you know that that faucet is not a face, you can't stop seeing the face. This is how apophenia works. The fact that AI also has apophenia is interesting. It's strange. It's something to follow. So, if AI is not only how it processes the world, but also how it senses the world, then the conjunction, the joining of machine vision and machine intelligence and interpretation becomes essential. Many of you maybe have used this. This is Google Translate's AR version of Google Translate. You hold your phone up to a sign or something. You tell it which language to look for, which language you want it to translate something into, and it will translate that for you, or it tries to. We're at an interesting moment with technology such as this in that they are good enough to use, but not good enough that they don't also make very strange mistakes. So this is a translation of a menu written at a Korean restaurant here in Moscow, translated from Russian into English. They're helpful. And it produces this very interesting poetry about food that is interesting and creative, but not necessarily appetizing, but that's okay. It may also give us secret messages. If it tries to translate something, it might suggest that you do an activity that could be dangerous, I suppose, here. Now, the question of machine vision is very interesting for us. When we talk about machine vision, it's important to understand, counterintuitive as it may seem, that today, most of the images that are made in the world are made by machines for other machines to look at. Most images are made by machines for other machines to look at. Machine vision is not a side thing. It's the majority of how images are produced in our world. And they are connected to certain kinds of interpreting intelligences that make sense of them. Images are a logistical infrastructure. This is also strange. So, we're also, I'm sorry, it doesn't look like this video loaded. Oh, there we go. More generally, the conjunction of a machine vision and artificial intelligence also brings us things like GANs, general adversarial networks, that are able to produce data that to us looks like an image, to produce images of things that are not real. None of these people exist. They are all produced out of the averaging of different faces in different ways. This is interesting. Also interesting then to us is the kinds of aesthetics that emerge from these. These aesthetics may begin as errors, glitches, mistakes, but in the accumulation of them, a new way of seeing emerges, a different kind of aesthetics that would not have existed before, and maybe even a new kind of image. For example, for artificial neural networks that are interpreting a lot of data to make an image or interpreting images to understand patterns within them, they may have hundreds or more layers that are interpreting this structure. If you ask that artificial neural network, for example, show me what's going on at layer 47 out of 100, where from the top to the bottom, just what's going on there, it may produce images like this that don't look anything like the input or the output. They're kind of like weird in-between thoughts that it's having about how to get from here to there. We don't have a name for this kind of image. The artist Trevor Paglen calls these neurots, but this is just a made-up word. But we need more made-up words because we don't have the words for the things we're making. Another good one, another good made-up word, is a classifier image. A classifier image is what happens when You train an artificial neural network to find something. It's really good at finding that. Let's say a dog, and you can show it 10,000 images, and it will tell you which ones have a dog and which don't, and it's 100. It gets it it's very, very good. And then you ask it an interesting question. You say, show me then an image of everything that is dog-like minus everything that is not dog. Based on your model, what do you get? That's called a classifier image. This is a shark. Train an artificial neural network that's trained to identify sharks in an image. It's very good at it. You ask it to show me what is shark minus what is not shark. You get something strange like this. Here are more classifier images. To us, I'll show you a little bit more up close. So to us, some of these don't look anything like the thing that they do. Again, all of these networks are very good at identifying these things from a range of images. But the core idea that they have of what that thing looks like is very different than us. It works. It's strange. It works in practice, but not in theory. It works, but we don't know why. We don't know how to think that way. Another strange thing is what's called universal adversarial perturbations. I'm sorry, but I don't have a nicer word for that. That's just what they're called. What this means is, on the left, you may have an image of a panda. This neural network is 57% sure that the image is a panda. But you do one simple thing. You just add that noise pattern, which is the perturbation in the middle, a tiny little bit, to produce the image on the right, which to us still looks like a panda. To the AI is 99% sure that that's a gibbon, ape. They're very easy to confuse. And this is because they think in a very strange and peculiar way. Here are more universal adversarial perturbations. It thinks that sock is an elephant, that those squirrels are a fox, that the dog is wool. Who's to say? So, outside the laboratory, the question of how machine vision sees and how it makes sense of what it sees is not an academic question. There's a few ways of thinking about how cities see in relationship to us. One is, how is the city looking at you through the lens of machine vision and artificial intelligence, surveillance, other kinds of things. Another is how you look at the city through the lens of machine vision and artificial intelligence, how it becomes a different lens for you. One of the questions we're asking then is not how, in a research project that we began at SciArc, the architecture school in Los Angeles, with my colleague Casey Rem, as part of research undertaken with the Google Artificial Machine Intelligence Group, is not how the city sees us or how we see the city, but how the city sees itself. Let me explain what I mean. So this is an example of how an autonomous vehicle, driverless car, sees the city. It uses LiDAR, it uses regular cameras, it uses any number of technologies to try to get an image of what's going on around it. But it doesn't work very well if you only have one car. When you have one car trying to figure out the world around it, and it can't collaborate with all the other cars around it, it tends to get lost in its own world. Same for us, perhaps, in a way. And so how do we address this? 5G, what are called 5G wireless technologies, will allow for communication between things in the city that is much faster, much more reliable than current networks. And this will allow for what we call, for example, collaborative vision. So remember when I said you may have one sensor that has two AIs or two AIs on one sensor, and these can get mixed together? That's how this will work. You may have one car that is sort of sure that the thing it's looking at is a person or a car, but the other car is very, very sure that the same thing that they're both looking at is actually a person because it has a better view. And so it can share its conclusion with the other car. They can, in fact, share vision and come to the same conclusion. This is also strange and also interesting. Now, there's more everyday ways in which we think about machine vision working in the city. Sometimes we don't even think of it as being about machine vision. QR codes, for example. These little, speaking of evolution, these little black and white flowers began blooming all over our cities, particularly in China, in relationship to an invasive species of the camera that people began to carry around with them. This flower would solicit pollination of money from this invasive species. Now, QR codes like this are also used as trackers. They're used as ways that augmented reality, which I'll talk a bit about now, is able to put an object or something on the world, and it knows where to put it. And I'll show you an example. The problem is that QR codes are actually really terrible markers. They're good for just a quick scan, but they're too regular. They're actually too regular in the pattern to actually work very reliably as a marker. And so if you want to have a more reliable and reliable QR marker where you can put something on an object and the AR overlay will actually work properly, we need a different kind of surface. We need a different kind of surface for machine vision to work right, for it to be able to see the city in the way we want it to see the city so that we can do interesting and strange things with it. So one of the questions that we asked with this project at SciArc was, what would cities look like if good machine vision tracking was a primary design consideration? What if we did transform the surfaces of cities so that they were designed for machine vision? What would the city look like? So we began with a couple I'm not going to show, the work is still in progress, and some of it we won't be able to show here right now, so a lot of this, but this is some of our preliminary research. One of the first things we did was to try to not deal with the whole city at once, but with a section of the city. And so we picked an area in downtown Los Angeles, and we developed we did a LiDAR scan of the entire section of downtown Los Angeles, all of the buildings, it was one of the most complete urban LiDAR scans done within this research context. You see some of these are just screenshots from a very, 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 very dense point cloud model. Here is an overview of the entire point cloud of the entire city region. The file would actually include all of these points would be bigger than I could likely run on our laptop here. So here is just a screenshot. But so the first thing is we get a good model of what the space is that we're talking about. We then started looking at possible marker strategies within the city, And one of the ideas that we had was that we may, sooner than we think, have to think about machine vision and AR as a zoning problem. Like, where will it be allowed? Where should it not be allowed? In what circumstances would it be actually dangerous for this to happen? In what places should we prevent this from happening altogether? You may remember some controversies about Pokemon Go, which was a early successful urban augmented reality application where people wandered into places where they may not have been welcome. So here's some other tests of these particular ways they work. Now, we then began building a number of neural network models to try to track how the surfaces that we have perform as trackers. What kind of surfaces work and what kind of surfaces don't work at all as trackers for this. And unfortunately, we found that most of the surfaces that you might find in the city, especially glass, are terrible for trackers. So initial test of trying to do this, we re-optimized the neural network in a few different ways to try to make it work, and we got some slight improvements, but clear that in order for AR, augmented reality, to work on surfaces of cities, we either need different surfaces or we need to train machine vision to see those surfaces differently than they do. One of the interesting and perhaps unfortunate things we also figured out was that the worst performing surfaces, the ones that were least useful, were the ones at the ground floor, which is where, in principle, you might want them the most. So let me just show you, this is all very preliminary, but let me show you some of the things we did, some of the initial tests. The idea here is, instead of changing the surface, let's figure out how to change the way the machine vision sees the surface so the surface could function better as a tracker. And so we basically trained the neural network to deform the surface, deform the way it sees the surface in different ways, and then tested that deformed surface as a tracker. And whatever worked, that would, again, retrain the network. And so we kind of were a bit hands-off. Whatever worked, worked. However the neural network changed the surface, that we got better results as a tracker, that's what we went with. These are some of the kinds of surfaces that do work as trackers very, very well. And then we trained it again, and it started doing this very interesting thing, where after we retrained it again, it started to introduce this circular grid on top of the surface. So this previous image here, we got about 90% success, where everything would work fine. This was more like 98%. And we didn't intend to do this circular grid on top of it. The neural network just introduced this on its own in relationship to being trained for the ability to adapt as markers. And so this may be what the surfaces of our cities end up looking like if we want them to be good kinds of trackers. This is taking a similar trained model, and what this would look like basically as a facade rendered in elevation. So here's some of the before and after images. On the left would be the surface as we found it. On the right, the surface as it appears to trained for the network. So again, this is all quite preliminary. And then just for fun, we said, well, what would it look like if we trained everything in relationship to optimization as a tracker? So if everything was the best tracker it could be, there's where we would live. So let me conclude then with a couple more maybe bigger picture remarks, and then I'll very happy to welcome Molly to stage. the question for our work really, this dynamic of camouflage and display, that what we're showing here is a way in which the city might evolve in order to be seen, but it may also evolve in order to not be seen. And that dynamic of camouflage, display, camouflage won't stop. It will continue. We'll be part of this process as well. But it may end up with producing cities that make perfect sense, but still look strange to us. And that's okay. It has to do really with, to me, inventing new kinds of abstraction. Abstraction, in this sense, is about the reduction of a condition to a form through one which might represent other conditions through which that is drawn. AI and machine vision is capable of its own kinds of abstractions. I don't mean abstract shapes. I mean abstraction of concepts that become shapes. And in order to negotiate this, to really, I think, make sense of it, we have to get out of the idea that AI and machine vision is only a tool for us, that for it to work well, even for us, that it must be more human-like. The most interesting things, the most beneficial things that AI is likely to bring, if we want it, are things that are not like us and which may, at first glance, seem very strange. We must embrace this. Should complex AI arrive, it will not be human-like unless we insist that it pretend to be so. Because, one assumes, the idea that intelligence could be both real and inhuman at the same time is somehow morally or psychologically intolerable. Instead of nurturing this bigotry, we would do better to allow that in our universe, thinking is a much more diverse, even alien than our particular case. The real philosophical lessons of AI will have less to do with humans teaching machines how to think than with machines teaching humans a fuller and truer range of what thinking can be. Thank you. Do you want to, I would like to introduce Molly. I want to make sure her keynote is ready to go. So if I could ask your help in that, yeah. All good? Okay, so let me introduce you real quick, if that's okay. Yeah. All right, it is my sincere pleasure to welcome not only to this event, not only to Strelka, but also to Moscow, my friend and longtime friend and colleague, Molly Wright Steenson. Molly Steenson is the Senior Associate Dean for Research at the College of Fine Arts. She is the at Carnegie Mellon University in Pittsburgh, where she is also the K&L Gates Associate Professor of Ethics and Computational Technologies, as well as an Associate Professor in the School of Design. One of her recent books, Architectural Intelligence, How Designers and Architects Created the Digital Landscape, is one of, I think, the most interesting, creative, and important histories of AI and of architecture, and especially their intertwining together, that we could hope for. And so it's my real pleasure to share the stage with Molly.
Hello. Let's see, I need to get back to the beginning here. Aha. I don't think I have ever given a talk wearing a blanket before. I grew up in a very cold place. I grew up in Minnesota, and yet here I am in Moscow in summer wearing a blanket. So excuse the fashion. All right. Great. The last time I gave a talk with Benjamin Bratton was in 2010. We both spoke at South by Southwest in Austin, Texas. And we gave a talk called Urban Technology on the Dark Side. And we wondered whether we should do the talk again tonight now that we know, of course, urban technology is dark. At that point in time, people seemed to be more optimistic about it. I don't know, maybe this is the talk that we are giving, both of us. But I'm going to talk about world building, artificial intelligence, architecture, and design. But I want to start with one question, which is, what is AI anyways? My friend Despina Papadopoulos, who is a wearable designer and a PhD student in philosophy at the Royal College of Art in London, tells me that AI is just another word for software. That makes me think of the Janis Joplin lyric, "Freedom's just another word for nothing left to lose." If I look up what AI is on Google image search, I get images that look like this. A lot of vector heads and rays, a lot of blue circuit boards. There's this figure beholding the hand. My student, Jae Ha, who is from South Korea, did an image pull, did a color pull on these images, and he said that these colors and shapes are quite familiar when I think of AI, because they're cold and impersonal and lonely. If we look at them a little bit again, and you'll see here at the top that there are different ways you can zoom in, and you can learn more about what these images are by category. And here you see things like human and female as different distinctions. Not man, but human and female. And if you zoom in and look at the female images, this is what AI and female looks like. And you start seeing other words here. You see words like sci-fi, bot, dark, and evil when you look at women and AI. And maybe that's not a surprise. You see this particular lady, I like to call her Cyborg Lady. And I think this is jQuery, the JavaScript programming language that you see in the background. I'm not sure why she stands for artificial intelligence. But she's got some different jobs. She gets used on the internet in all sorts of ways. So this first one says, Brits fear the AI future. And the second one indicates that maybe she has a job at IBM Watson, the ingredient brand helping inform the purposeful business of tomorrow. And the third suggests that she's got a job at IKEA, artificial intelligence embedded in furniture. IKEA is considering. And this is the woman that stands in for all of these things. Maybe it's not a surprise that when we see AI depicted in films, we see things like Ex Machina, what we could call the fembot model, the robot intelligence that is evil and maybe imprisoned, but then breaks free. And I hope it's not a spoiler if you haven't seen the movie. I think probably everyone has at this point. But she leaves her captors behind. Or there's the AI in this mode. This is from the movie Her, and here is Theodore, who is having a relationship with his operating system. And she's played by Scarlett Johansson. And you only encounter her as a voice that he hears in his ear throughout the movie. And he has a close relationship with what is considered to be an AI. We know what this looks like. This is Minority Report. And the interfaces in Minority Report were designed by John Underkoffler, who did a master's and a PhD at MIT, the Massachusetts Institute of Technology, where his research was about the future of holograms. A lot of these ideas are really old. You might be familiar with the play Rossum's Universal Robots, which came out in 1921. This particular version here that you see right here is from the Berlin production in 1923, and Friedrich Giesler did the set design. And probably, thank you. I think I've warmed up. And probably the best known version of filmic AI, HAL 9000, who warns us, I'm sorry, Dave, I can't do that. HAL is 51 years old as of this year. Again, when we go back and ask Google what AI is, we find all sorts of things. We find out that AI is the new. It's the new black. It's the new user interface. It's the next digital frontier. AI is the new electricity. And apparently, Andrew Ng is running for president in the United States. AI is dreaming up all kinds of new video games, according to this particular article. And I just point out that I highlighted the word new, and it showed up 6 times, although one of those times is New York, so it doesn't really count. Google's AI is a new paradigm that unites humans and machines. And apparently, I am also a new AI. But the fact is, and I think it's worth returning to this, AI isn't the new anything, because AI isn't new. The term artificial intelligence was first coined in 1955 by John McCarthy, who was the co-founder of the MIT Artificial Intelligence Lab. And he described AI as making machines do things that would require intelligence if done by people. The idea had already been around, some say since the 1st century in Egypt, going back thousands of years, but more recently that it was a question coming out of information theory and information theory and cybernetics. Benjamin just talked about Alan Turing, and Alan Turing wrote in 1950 that he proposed to consider the question, can a machine think? And he talked a little bit about the imitation game, the question of whether a human could be tricked into believing that a machine was in fact a human. In 1952, Arthur Samuel popularized the term machine learning to mean programming a digital computer to behave in a way which, if done by human beings or animals, would be described as involving the process of learning. He didn't invent the term, but he's the person who's most known for it. And what you see right here is a photograph of him playing checkers with a computer, which is how he got. That was the learning set that he used, the training set that he used was a set of checker moves. And in 1961, Marvin Minsky, who was the other co-founder of the MIT AI lab, said that, I believe we are on the threshold of an era that will be strongly influenced and quite possibly dominated by intelligent problem-solving machines. And what you see here is a set of block stacking machines that were able to find the edges of the blocks and then manipulate a robotic arm that was able to manipulate them. And that's why it gives me pause when people like Jeff Bezos of Amazon or Elon Musk declare an era of artificial intelligence in 2016, 17, 18, 19, and beyond. We've been doing this for a long time. World building is a part of this equation too. And you might wonder when architecture was going to begin to come in. In this particular talk, I'm not going to go into great detail about architectural precedents. I'm going to stay with AI. But I want to point out how far back some of these ideas go as well. First of all, if we take the very notion of computer architecture, this is an idea that goes back to 1962, or again, the mid-1950s. Frederick Brooks wrote that computer architecture, like other architecture, is the art of determining the needs of the user of a structure and then designing to meet those needs as effectively as possible within economic and technological constraints. And he was talking about the IBM Stretch computer, which is what you see here. It was a terrible failure. It went way over budget, and people lost their job over it, except what survived from that computer, from that project, was its architecture. And it went on to form the core of the IBM System 360 computer, which is one of the most successful computers in IBM history. So computer architectures are replicable, and they live on, and they provide a foundation on which we can build worlds. But we could also look at the work of Douglas Engelbart. And many of you probably know who he is. You know that he invented the computer mouse. Here's an early prototype of it made in a steel wheel and wood, and the patent drawing for it. But I'm struck by something that he wrote also in 1962, which was a report called Augmenting Human Intellect, a Conceptual Framework. And in this long report, he put forth what would be an eventual interactive computer system. And he would bring this to life when he did the mother of all demos in 1968, which was a demonstration of hypertext and voice recognition and a bunch of different things. Here's an image of him doing that demo. He talks about world building, and he talks about architecture in the very first pages of the report. And there he writes, "Let us consider an augmented architect at work. He sits at a working station that has a visual display screen some 3 feet on a side. This is his working surface and is controlled by a computer with which he can communicate by means of a small keyboard and various other devices." So he's got an architect. He didn't know very much about architecture. Why did he turn to architecture? Architecture is about building worlds, and Engelbart was building a world. Okay, so maybe it's worth a bit of discussion about what we mean by intelligence. If I look it up in the Oxford English Dictionary, which is one of my favorite things to look up because of the etymological definitions of things, we see words like understanding and comprehension, quickness. We know that intelligence is a rational being or an alien intelligence. We know that intelligence is about obtaining or exchanging information. We know that it's about learning and adapting, and this was really important for the history of AI. We see it in the ideas of people like Alan Turing, and we see it in different notions of cybernetics throughout the 50s and 60s, and indeed we see it today when we talk about machine learning. If we go back to Alan Turing again, he wrote in 1950 in that same article in which he introduced the imitation game, presumably the child brain is something like a notebook as one buys it from the stationers. Rather little mechanism and lots of blank sheets. I also like this idea very much. This is J.C.R. Licklider, and for years, an article that he wrote called Man-Computer Symbiosis put in place all understanding that we really had of what interactivity could be. really for decades. And when we talk about ideas of AI and symbiosis, which is a word that floats around Silicon Valley all too frequently, it's coming from this man in this article in 1960. He wrote that human-computer symbiosis will involve very close coupling between the human and the electronic members of the partnership. The idea that together, the entity, the assemblage, is greater than either part on its own, something I think that Benjamin highlighted in a lot of different ways in his talk. We also know that intelligence is reason, learning, and surprise. Something is intelligent when it surprises us. Marvin Minsky, again, said, "To me, intelligence seems to denote little more than the complex of performances which we happen to respect but do not understand." So if we like what it does, but we don't get it, we don't understand it, then we think it's intelligent. Again, another concept that's quite old. We've talked a little bit about the notion of the uncanny valley, and Benjamin has talked about the reverse uncanny valley. But I want to introduce it again here so we can take a look at it. The uncanny valley was published in an article in 1970 by Masahiro Mori. If you look it up online, you should be able to find it. And it talks about the fact that things that are too lifelike but not human freak us out. They make us uncomfortable. They feel eerie. And Mori said something about this that I think is really interesting, not for the things that make us feel eerie, but what they teach us about ourselves. He said, "We should begin to build an accurate map of the uncanny valley so that through robotics research, we can come to understand what makes us human. We use this as a way to understand who we are and why we react in the ways that we do, what happens in that valley as we move through it." But I want to suggest a couple of other things. I'm a very big fan of a woman named Janelle Shane. She has a website called AI Weirdness, and she trains neural nets to do very funny things. And I think that she's the best, most subversive thing going on. And in this particular case, she was analyzing how particular image recognition algorithms saw certain things in certain images. So she fed this first picture to a Microsoft Azure algorithm, and it reported back that this is a picture of a hillside next to a rocky hill. And the tags that it includes are hillside, grazing, sheep, giraffe, and herd. Do you see any sheep or giraffes in this picture? I don't see any. And she realized that typically when you see a green meadow next to rocks, there are sheep. So the image recognition algorithm has started hallucinating sheep where there are none. So she decided to play with this a little bit. And she took a picture of some sheep in a field and colored them orange and fed it to the algorithm. And it reported back that this is a group of orange flowers in a field. No longer sheep because they're orange. And then she got another picture of goats in a tree. Indeed, those are goats. And fed it to the algorithm. And it read back that Neural Talk 2 said that it was a flock of birds flying in the air. And Microsoft Azure said it was a group of giraffes standing next to a tree. Here's what she said about these algorithms and her experiments with them. "If life plays by the rules, image recognition works well. But as soon as people or sheep do something unexpected, the algorithms show their weaknesses." I think this is important at this moment in time for some reasons that we could see at other points in time in history, such as when Marcel Duchamp, or possibly Baroness Elsa von Freytag-Loringhofen, dropped off this particular urinal at an art show and called it Fountain and signed it Armut. And this was an important moment for how we saw art. Or when we look at Dadaism in the 19-teens as pushback against World War I and what to do in a time when the world makes no sense, and so neither can art. Or similarly, the work of someone like Eugene Ionesco, who wrote the play Rhinoceros, in which a set of people, a group of people in a French village, one by one turn into rhinoceroses. And this play was first performed in Dusseldorf, Germany in 1959. It's a play about totalitarianism and its threat. And in his crazy plays where very strange things happen, they're intended to make you think about the current moment. And certainly I find myself using these goofy things that we can use with neural nets as a way to turn upside down how we understand the world. So I want to talk a little bit about the world that I live in and where I'm from. I live in Pittsburgh, Pennsylvania, and it is a city that was founded in 1787, which is quite old for American standards. It is a city of the future in ways you might not expect. About a kilometer from my house is the National Robotics Engineering Center and Carnegie Robotics. And these are places that I go by and walk my dog or see when I go on runs. And sometimes at night, when my husband and I go out and walk the dog, we see kind of empty territory like this. This is Carnegie Robotics in the background that you see, and this is a vacant lot that was about to become developed. This is a photograph we shot. This is what that same area looks like a little bit later, about a month later, via Google Street View. And then it became this, which is a pretty unassuming sort of urban, suburban park, technical park called Tech Forge. And this is one place where Caterpillar has its offices for autonomous vehicles for construction. They make autonomous bulldozers and dump trucks and backhoes. Similarly, we could go another 2 kilometers away into what we call the Strip District, and we'd see this. This is another Google Street View image, which grows up to be Argo AI, which is an autonomous vehicle startup that was bought for $1 billion by Ford and has just forged a new relationship with Carnegie Mellon that was announced this week for a $30 million research center. When you visit the landscape of Argo's website, you see an Argo vehicle driving across one of Pittsburgh's many bridges. And I should say that we see vehicles like this all the time. Many times a day, prototype autonomous vehicles go by us all the time. And we also see Uber's Advanced Technology Group. This is in the same neighborhood, again, 2 kilometers from my house. And this is the building right here in the background. I like this page on the Caterpillar website that says, "Perception is everything," while talking about autonomous vehicles and autonomous construction. Because these are the kinds of images that my husband and I shoot at night when we're out walking the dog, and we peer in and we see the backhoe parked here with a picture of itself. And we got closer and we got another image. And I found myself thinking, this reminds me of Max Ernst and one of my favorite paintings of his, which is Lop Lop introduces Lop Lop. Lop Lop stellt Lop Lop vor. And lop lop statt lop lop vor is Max Ernst's subconscious, more or less. He's introducing himself in a motif that follows through many of his paintings. I feel like this looks somewhat familiar. Benjamin asked this as well. Whose intelligence? This is my dog. His name is Emoji. He's a good boy. He's very smart. And he's got intelligence and ways of knowing that surprise me all the time. I refer to this instead of if this, then that. I call it if this, then dog. He knows when I'm going to leave before I know that I'm going to leave. We could also have swarm intelligence, and there are people who study how bees are intelligent, and there are notions of collective intelligence, how we can bring this all together in new kinds of ways of being, into new assemblages of all of the above. And so we find ourselves again back in my neighborhood, and this is my house, the one right here in the middle, via Google Street View. And when you look closely, there's my dog, and there's my mother-in-law on Google Street View. And I realize my dog is looking back at the Google Street View car. And these are our autonomous landscapes in my city of the future with my 135-year-old house. There are so many things that we can't get robots to do right. We can't get them to pick raspberries because they crush them. And when we perfect algorithms so that they move perfectly, that they move vehicles perfectly, they dig themselves into ruts because there's not enough noise to get them out and keep them moving. If I return again to Google Street View, Google Image Search, to look at what the future is, this is what it tells me. This is what cities of the future look like. And there's a futurist named Lisa K. Solomon who points out the future doesn't have to be something that happens to us. There are many potential futures. There are choices we can make. But I also want to point out a couple of things. How we model intelligence, and in that future, how we model intelligence, impacts the nature of the input and the output. We've talked a lot today here at Strelka through the various projects of the new normal about natures of inputs and outputs and models. I think this bears a little bit of thought. These are important to us as people interested in culture because they're a matter of how we build knowledge. They are questions of epistemology. And they're a measure of how we understand who we are. And when I round the corner to go to work, I pass this billboard. And Carnegie Robotics reminds me, we're still hiring humans. Thank you.